Bismillahirrahmanirrahim. Today we will discuss natural exponential functions. The first slide gives a hint about what we will be discussing about. This slide on the left one shows the thermodilution method, where it is actually represented correlating the time to temperature, but this the slide will be reversed to show the process. So this is the real slide, and we will show later on in a reversed way to show why did we do such. This is the endocyanine green injected in the heart, going through the chambers of the heart, and then creating a dilution in concentration, and we can create an area knowing by time. And this the area can be utilized to measure the cardiac output. This is the endocyanine green injected, and this is the fluorescent exposed, and this is the camera which we can record the decrease in concentration. This is different concentration of endocyanine green. In the previous chapter, I was discussing gas laws, and I made a mistake where I told that whenever I want to fill a carbon dioxide cylinder with oxygen, I begin first of all to fill it with oxygen 10%, which is completely wrong. I had to tell you that I begin with filling the cylinder with carbon dioxide 10% till the pressure reaches the 10% of the total, which is 13.7, and then I fill the rest of the cylinder by oxygen to gain the total 137 bar pressure of the cylinder. This is how we are utilizing the Dalton's law. This is what I want to tell you about the previous slide. The natural exponential function is a tough subject. So we will begin in the first slide by representing three items. First of all, the conception of the exponential function. First of all, what's the meaning of a linear curve? Linear curve, it's represented, as we can see, from an x and an x and y axis, and then it is represented as if I am filling a tap with water. Of course, whenever the tap is being increased, of course, by time, we can make a correlation between time and volume, and we can see that we are gaining a straight line. This line is called linear, representing of a curve. On the other hand, if I fill the tap at the same time, and then I open the plug hole on the beneath the tap, and I let the water go out. See, so we will find by time that the curve will be declined such a way as an exponential, as we can see. First of all, of course, because the head of the pressure is much increased, because the volume is much increased, and the flow by time is increased. So the pressure here in these two correlations are utilized to make a correlation between that the flow of water at any time is correlated to the amount of water present. So this is what we call exponential. This what makes the curve descend in such a way. Of course, it never reaches zero. It's an infinite process, you see. So expressing the exponential function, it is a rate of change of the quantity, the rate of change of quantity at any time, which is proportional to the quantity at that time, you see. So the rate of flow is proportional to the amount present, you see, quantity to quantity, volume to volume, you see. We can represent this in anesthesia. Whenever I fill the lung by time, if the pressure is constant, by a way, of course, of the pillows, you see that during expiration, filling is in a straight line, in a linear line, the correlation between volume and time. And then when the patient expires, first of all, there is a lot amount of air coming out, and then by time it becomes less speedy while it is emptying, you see. So this is an exponential process during expiration. This is made of the elastic recoil of the tissues of the lung, of course, the compliance, which makes the capability of the lungs to exhale. So this is a representation in an anesthetic way. How do we create an exponential function? The second thing is washout curves. Washout curve, it is also an exponential process. This we have the same sink and we have the plug hole of the same at the same time, and we have watering going through. But the point that the water is laminar, and I must make the rate of water coming out equal to the water coming down from the sink after opening the plug hole, you see. And then we put an even distributed mudness. We create a mudness situation in such a volume. Of course, this volume I can gain the quantity of the mud knowing the concentration. If we multiply, of course, the concentration by the volume, we can get the quantity. So whenever I open the plug and then I begin to make the water come out, by time, definitely the concentration of the mud in the top will be correlated to the concentration coming out. See, so this is represented by the exponential equation, that the quantity of flow of the dye at any time is correlated to the quantity of the mud, present in the sink. So this is an exponential process. The exponential process never reaches zero because the level of the plug hole is at the same level of the sink. You see, this is why we have an infinite time. It never ends to zero. So we will gain out of this washout curves, as we can see, 4 points. First of all, we can utilize it to measure the cardiac output, but what we call the endocyanin green, which is dye being injected to the right side of the heart. So it is an invasive by pulmonary catheter, and then this dye circulates in the heart, and this chambers of, as if it is the sink, it goes through, and the concentration by time is being decreased. This concentration, is being taken from the artery, where we can use the spectrophotometric method to measure the concentration, where we can create a curve, as we can see, correlating the concentration by time. This curve, if it is semi-logarithmic, what's the meaning of semi-logarithmic? It is a curve where the y-axis is semi-logarithmic and the xy axis is linear. What's the meaning of semi-logarithmic? That the distance between the points are not equal. So suppose we have 1 to 1.5, and then we reach to 2 and 3 and so on. So this is what we call, if we create such a curve, we can utilize or get a curve as shown in front of us. It first of all, of course, the endocyanin is being increased in the circulation and begins to descend in an exponential way. But while it's descending, it becomes elevated again, creating what we call a hump. Why? Because there is a recirculation. So to solve the problem, as we said, we create a semi-logarithmic curve, and then I extend the line downwards to create an area. This area, through it, I can measure the cardiac output. The point that's to be mentioned was the meaning of that the semi-logarithmic curve doesn't have the y-axis doesn't have a zero. You see, so there will be a fallacy. So we ought to descend the area downwards below the level of the x, so to reach the zero of the y. This is why you must make compensation in case of measuring the cardiac output. Or on the other hand, we can use microprocessors to estimate the cardiac output. These are different curves correlating the cardiac output, whether it's 4 liters per minute or 8 liters per minute. So this is the first method to measure the cardiac output. We call dye dilution method. But as we said before, it's has a hump, which makes the curve complicated, and we cannot repeat it. You see, the second thing is the thermal dilution method, which is the famous one used, where we used pulmonary catheter has two routes, or of course we can use the Swan-Ganz catheter. The first route reaches the right atrium or the superior vena cava, and the second one is utilized to have a thermistor. A thermistor is a device present to measure the temperature. So we have a probe in the right atrium, and we have another probe in the pulmonary circulation to measure the temperature changes. So whenever I inject 10 cc of glucose 0 degree to the circulation, of course, it becomes warm, reaching the pulmonary artery. This change in the warmness or the temperature, I can utilize it to correlate the time per pressure, utilizing this area to measure the cardiac output. This method, of course, can be repeated at the same time. We don't have what we had before, which is the hump. The nitrogen washout technique. Of course, nitrogen is present in our body. Whenever I want to expire this nitrogen, I expire this nitrogen by time, reaching from 1% to finally 2.5%. This is the final concentration that I can gain during expiration within 7 minutes. So whenever this figure is fulfilled, I can say that there is the equal distribution among radiation in the lung. The fourth thing is the radioactive decay of any substance, radioactive, whenever it's injected. By time it becomes less in concentration, which you can measure by scintillation. This is a wash out curve where we can measure, suppose the cardiac output, whatever. Duration of exponential process, as we said before, this duration is infinite. This is the problem, that I can notice the proper time. So instead, we imagine that this curve is using what we call the half time. The half time is the time taking for the subject to subject injected or whatever to decrease to the half of its percent. You see, and so on, the fourth of it, the quarter of it, and so on. So we create different half times. We can see from the graph. You see, this is what we call half time, and of course, it has been utilized in radioisotope studies. The second is what we call the time constant. The time constant, the definition is some sort of difficulty, where I wanted to tell you that if imagine that this process continued, we could have figured out it in a much better way, but instead we use what we call the constant, the time constant, where we divide the period as much as we can to different figures. You see, we have first and the second and so forth time constant. So in case of the expiration of the patient, of course, we can say that the expiration of the patient takes around 1 second. So we have 3 time constant. Each of them is 0.3 seconds. So this is the normal expiration of the patient, where it takes around 1 second, and it is of course an exponential process. The first time constant takes around 37% of the volume of what we are going to measure, and of course the second one takes 37. Then we reach what we call 90%. Of course, we ought to leave the 5% because the curve is never infinite. It doesn't go to 0. You see. Of course, as we said, normally that the expiration takes 1 second, and we have 3 time constant. We don't have to do anything, but in case we have the time constant, first of all, is called ta, and ta is regarding respiration is the multiplication of the compliance times resistance. Of course, we know the resistance is about 0.6 and compliance about 0.6. If you multiply both of them, will yield the 0.3 that we mentioned before. See, so if we have a problem, a patient with has a low compliance, we can hasten the period of inspiration whenever the patient is on a ventilator. And if we have a resistance, as we can see, the time constant is very prolonged. We can prolong the period for that the patient can inhale all the amount of expiration present. After that, we have what we call the exponential formula. Of course, exponential process made of an exponent, يعني أسي. You have a figure, and then we have a figure up of this figure. You see, so in case of this fixed exponent, exponent means an index. So x time 2 means that the exponent is 2. This is fixed. In case of a variable one, we have an exponent which is x on top of k. You see, so this k is figured out to be such a figure, and then it is also called e. The x is being or the k is being represented by e. So this is a figure where I can utilize this variable exponent, where I can figure out how much of the volume present at any time during expiration. So whenever I expire from the functional residual capacity, I can figure out at any time how much the volume at that time, knowing the compliance and the radius and the resistance and the time, and of course we know the figure of E, which we had said before. From this equation, I figure out the volume at any time. You see, this is how I'm trying to represent what's the meaning of a variable exponent. You see, the point is the positive exponential process. Of course, all exponential process that we had mentioned before is negative. But if we have, suppose, a growth of a bacteria in a proper nutrient media, of course, the bacteria will nourish in a speedy way, representing curves such a way. Curves. How does it comes up from 0 to upwards, or the cancer spread of cells? You see, so this we call it a positive exponential process. You see. Now comes what we call the built-up exponential process. It must not be confused with what we call the positive exponential process, because the process goes in such a way from 0 upwards in a build-up. But this is not a build-up. You see, this not to be confused with what we call the positive exponential. This curve represents how the concentration of nitrous oxide or isoflurane or fluorescein reaches the alveoli through inspiration. You see, so whenever I inspire whatever the concentration, the inspired goes to the alveoli, and at the alveoli, of course, the circulation takes some of this inhalation anesthetic. So whenever, of course, the circulation takes more, we will fail to build up a final concentration of the anesthetic in the alveoli. This is what we call the build up. We are building up curves, and then we will find that suppose after 5 seconds the inhalation concentration of nitric oxide reaches the lung in 5 seconds, but other inhalation takes a longer time. This is what we call the build up exponent. We can represent this build up by as we see two filling containers, one on the left and one on the right. There is a head of pressure difference. Of course, through this plug hole, the water will go from this side to the other side by the head of the pressure. So we can find that this is a negative exponential process, and this is a positive exponential process, or it is a build-up exponential process. You see? The second thing regarding the built-up exponential process is the built-up exponential correlated to anesthesia. You see, we call it a wash-in instead of wash-out because we are building in. We are increasing. You see, so if we have a patient, as you can see, on a ventilator, and we can build up an exponential curve, which is a build-up exponential curve, as you can see by time. It first of all it increases slowly and then becomes speedy till it reaches a final destination. So this is what we call a build-up exponential process. But as a matter of fact, there are other things that control this exponential, because whenever inhale anesthetics, of course there is a circulation which takes some of anesthetic, so it will affect the final exponential, or in other words, there are several exponential processes during the uptake of the anesthetics, and it can be represented by this curve. This is the normal exponential curve, and then we can analyze this exponential curve into 3 components, A, B, C, because we know that this exponential is affected by multiple factors. You see, the drug is being affected by taking off by circulation and so forth. So it is not a simple exponential, but it is a multiple exponential process. This figure on the right side represents the how can we estimate the oral administered drug concentration in the GIT and on the plasma. Each of them has an exponential. So if we combine them to reach a final exponential process, it can be divided into its components. And this is why whenever I want to, of course, the absorption of an oral supposed tablets it reaches to the tissue in an exponential way. What's the meaning of that? That whenever it's in the intestine, it goes to the circulation exponentially. First of all, it's increased in rate of uptake, and then it becomes decreasing. And in the plasma, this is the point that's complicated, because we have a problem of elimination and metabolism of the drug in the plasma. So there is a several exponential processes dealing in the blood, or it is a complicated process. So this makes the curves. You see, I want to assure that whenever I take a drug, I must maintain a plasma level. I must not exceed to a toxic level. This is why we must adjust the drugs to reach to such a ratio, or we can use instead a syringe pump. This, of course, represents all the exponential process during inhalation of anesthetic from the inspiratory concentration reaching to the alveoli and then finally the tissue. You see, it is an exponential process. You see, the washout curve that we had mentioned before several times, of course, it has a time constant. How can we measure the time constant of it? Dividing a volume by flow. The volume of flow by flow. This is the correlation between. I'm sorry, it's not present this slide. So this is the time constant figured out from a washout curve. So if I know the flow of the perfused fluid, and I know the time constant, I can figure out of the volume, and vice versa. You see, so I know it is a tough chapter. I hope that you understand. The most important is really how to measure the cardiac output methods by the dye dilution, the thermal dilution, and of course it can be utilized to be questioned in an MCQ. I am trying to improve myself. I hope that I succeeded, because I know it is a tough subject. Please ادعوا لي والسلام عليكم ورحمة الله وبركاته.